Hello and welcome back to another math video. Today we are talking about an introduction to set theory. So what is a set? A set is an unordered collection of objects called elements, and that is an intentionally pretty vague definition because a set can contain pretty much anything. It can be numbers, words, letters, objects, other sets, or a combination of all of these things. And there are lots of different ways to represent a set. One pretty simple way is just by drawing a circle and filling it with things. So let's put in the number 42. I'm going to put a star in, and how about the word math? And I can also write out that set by opening a curly brace and listing all the things in that set, comma separated, and closing that curly brace, and that would be referred to as list notation because we have listed every single element in the set, comma separated, and collected with curly braces. And we can name these sets. I'm going to call this set B by just writing equals to and then the name of that set. So I'm going to ask you to take a second and pause and give me the set A. We can call it set A. I guess you could call your set whatever you want, containing the elements 1, 2, and 3. So I'm going to erase my board and show you, hopefully, what that looks like. So I asked for the set A with the elements 1, 2, and 3. And that's how it would look in list notation. And that is how you'd represent that in formal math, probably not with the circle and a 1, 2, and 3 floating somewhere in it. So you would describe this set by saying A is the set containing the elements 1, 2, and 3. And we can actually describe the elements within a set by using this symbol. It is an epsilon, which just means is in or is a member or is an element of. This is a set membership symbol. And if we wanted to say an element was in a set, we could say 1 is in or 1 is an element of the set 1, 2, 3. Or we could say 1 is a member of the set A. Those are equivalent ways to write that. And then conversely, we can also say an element is not in a set by using that same set membership symbol with a diagonal slash through it to represent not in. So we could say the number 4 is not in the set A, or 4 is not an element of A. And that's a true statement, right? Because we can see pretty simply here that the set A only contains 1, 2, and 3. So sets can be finite, like we saw with our previous example of set A containing 1, 2, and 3. And sets can also be infinite. There are actually a number of sets that you may be familiar with that are infinite, like the set of all natural numbers. I'm going to define it with the smallest number starting at 1 all the way to infinity. Maybe you think the set of all natural numbers starts with 0. You are welcome to debate that in the comments down below. I'm going to say it starts with 1. Or you can say the set of all integers, -2, -1, 0, +1, +2, and so on. There are lots of infinite sets. See if you can name any other common infinite sets. When we're talking about finite and infinite sets, you might be wondering if we can describe the size of a set a little more precisely than just endless or it has an end. And we can. So the size or the cardinality of a set can be described using these two pipes around the name of a set. It's kind of like an absolute value. So we have the cardinality of A, that's how you would read that. And you would get the size of a set. One way you could do that is by counting simply all the elements in a set. So what is the cardinality or the size of set A? Well, I'm seeing 1, 2, 3 elements in there. So A has a cardinality of 3. Sets can have lots of different finite cardinalities. Our example set here, A, had a cardinality of 3, and we also know sets can be infinite, like the set of all natural numbers. What about a set with the cardinality of 0? Well, we actually have this thing called the empty set. It is represented using a 0 or an O with a line through it. You can also represent the empty set using 2 curly braces with nothing in them because the set is empty. And my question for you is, what is the cardinality of the empty set? I want you to pause and take a second to think about it. And we can figure this out. The way we figured out the cardinality of our example set A, how do we figure that out? Well, we counted the number of elements in A. We counted 1, 2, 3 elements. So A had a cardinality of 3. And we can do the same thing here with the empty set. We can count the number of elements in this empty set. Or maybe you can't count the number of elements in the empty set because there are no elements in the empty set. So in other words, the empty set has a cardinality of 0. And again, the notation, the curly braces or the 0 with the line through it, they are equivalent. So now I have a trickier question for you. Let's think about the set containing the empty set. And we mentioned at the beginning of this video very briefly that this is a valid set. It is a set containing another set. Sets can contain lots of things, including other sets. So the set containing the empty set, what's the cardinality of that set? I want you to pause and take a second to think about it. This is a pretty tricky question that trips people up their first time seeing it. Let's do the same thing we did above, where we counted the elements in the set to get the cardinality. So our example set A had 1, 2, 3 elements in it. Our empty set had 0 elements in it. How many elements are in the set containing the empty set? Well, I'm counting 1. And that's correct. The set containing the empty set has a cardinality of 1. And that element happens to be the empty set. So we can say the empty set is in the set containing the empty set. So describing sets can get kind of messy when you just list all the values because sometimes they get a lot more complicated than a simple 1, 2, 3, and so on. As a simple example, we can say we want the set of all even integers. And, well, we just described it in plain English. In list notation, you would probably open a curly brace. You'd say 2, 4, 6, and so on, and close that curly brace. But is there like a nicer way to write that? And there is. And we can describe it by giving an open curly brace and then giving some form that our values will take. A pipe, which represents such that it follows this rule, and then close that curly brace. So some form such that it follows some rule. And for even integers, I'm just going to tell you that the form is 2n such that n is an integer. And we can try this out and we can test it. And if we get even integers, then we've done something right. And if we get an odd integer, then we've done something wrong. So we can test this by plugging in valid values for n. And our rule is that we've limited n to all integers. So one integer for n I can think of is 1. And then it's going to follow the form 2n. So let's plug it into this formula 2n. So 2 times 1, which equals 2. And let's write down all the values we get. So we're going to start with 2, which so far so good. 2 is an even integer. And we can try n equals 2. And we can put it into the form 2n. So 2 times 2, which equals 4. And that also is a valid even integer. And the set of all integers doesn't limit us to only positive things. So let's try n equals -2. And let's put it in that form again, 2 times n. So 2 times -1, which equals -2. And -2 is also an even integer. And you can keep trying it, and you can keep plugging this in on your own, and if you get something that doesn't give you an even integer, please leave a comment down below telling us what the n is and what you ended up getting. And that is just another way to describe a set, and that is called set builder notation or predicate notation, where you give the reader the tools to build the set that you want. So you gave them some rule in some form that your values have to follow, and they'll be able to build it themselves or check it themselves the way we just did. And that is all for this intro on set theory. Thank you so much for listening. I hope you learned something new. And remember to keep on trucking.